Hello. Let's get started. Thanks for coming. Good to see you. Today I'm going to shift our focus from saccades, anatomy of saccades, and eye movements to tell you a little bit about the spinal cord, the basics of the anatomy of that system, and how you control movements of your body when it comes to things in the skeletal system, and show you a little bit about the engineering work that has been going on in building devices that augment and replace when there is damage to the spinal cord and spinal cord injury, giving patients the ability to continue moving despite the fact that the spinal cord has been damaged. Okay, so we're going to focus on the spinal cord and the control of movements as it comes to the spinal cord. So this is an illustration of the nerves that leave the spinal cord and go to various parts of the body. And here's an illustration of the spinal structure. This is a vertebra. You can feel the processes. If you put your hand behind your back, you can feel these things. This is a disc that separates the vertebra. Between the vertebra, you have this a cord that carries the nerves and houses neurons. It's called the spinal cord, and it's covered in a sheet called the dura. The dura also covers the brain. It's this leathery, thick insulation that separates the bone from the soft tissue that makes up the neurons. So the spinal cord is divided into four parts: the cervical here, the thoracic, the lumbar, and the sacral. If you look up here, you'll see that each nerve that leaves the spinal cord has a name: C1, C2, C3, C referring to cervical. And so, for example, the shoulder and the wrist are controlled by the nerve that leaves the spinal cord at the level of C6. So this is interesting, this is important, because when people have a car accident, when they get a neck transformation that results in a whiplash, the damage is most likely in C5 and C6. Yeah? It's hard to hear me. Oh, okay. Oh, yeah, the mic is on. Well, maybe this is not on. No, that one's definitely on. That one's on. You want me to increase the volume? I can do that. Let's see how this is. Is that any better? No? I'll try to speak louder. I'll speak towards you rather than to the floor. Sorry about that. So a car accident often results in a whiplash, and whiplash would produce a damage to the nerves that leave the cervical region, C5 and C6. And what do they control? They control wrist movements, elbow movements, and shoulder movements. And a little bit above it, you have breathing and head and neck movements and heart rate. It's very important stuff. So, and the finger movements are down here. So we're going to get paralysis if there's damage here. And so it makes it so that there's nothing below that can be controlled by the brain anymore. And I'll show you a little bit of more about that in just a minute. But first I want to point out to you that the breathing is coming out of these cervical regions that are way up high, C1, C2, C3, and C4. But of course your breathing apparatus is down here, your lungs, and your intercostal muscles, and your diaphragm is down here. But the nerve that's leaving the spinal cord that's going to travel to control your diaphragm leaves it very high up. And you might ask the question, why? You know, why does the nerve that's going to control the diaphragm, that's going to control your breathing, leaves the spinal cord at the level of the C2, C3 cervical segment? And the answer is that basically we understand nothing about biology except in the light of evolution. And what you're seeing is an example of a vestigial history of our species, which long time ago, didn't used to breathe with our lungs. This used to breathe with gills. Fish. And that nerve just got extended and went down to the place that eventually became the breathing apparatus. Okay, so at the spinal cord, here's an image of it. Slicing through the spinal cord this way and looking at it from the top. The back is here, the dorsal surface. The front, the gray matter, you have the ventral surface. And in this case, what you're seeing is an example of a nerve that's coming from the hand. And what I want you to notice is that the nerve comes in, here's the cell body of the nerve, and then it goes, the axon gives rise to a process that goes through the dorsal surface. So the input to the spinal cord is coming from the back, the dorsal surface. And then it makes synapses to neurons here. And then there's a motor neuron in the ventral surface, which then sends its axon out to the muscle, let's say, of the hand. So the dorsal root houses the cell bodies for the afferents meaning inputs to the spinal cord. And then the efferents, the part that is sending information out, the motor neurons, are residing in the ventral root. Here are the nerves that run up and down the spinal cord, sending information to the brain, receiving information from the brain, and then inside this butterfly region here is the gray matter, where the cell bodies lie. This is where the neurons have their cell body. Over here, the white matter, outside of this butterfly region, that's where the axons go up and down, providing information above or sending information below. Now, over here, there's a blow up of this little part of this axon here. So here's an axon that's running up and down, and what you're seeing here is a little blow up of it where you have a glia cell, which is called the oligodendrocyte, that's providing myelin for the axon. So this is like insulation. The myelin allows the axon to produce those action potentials and not have it die out, essentially. So without the myelin, the action potential will fade away. With the myelin, you have the opportunity to transmit the action potential up and down the axon without decay. Yeah?
Doesn't it also increase the speed of the action potential?
Yeah, it does that as well. Right. So the reason why I bring up the myelin and the glia cells is because we're going to see that that's one of the main problems in spinal cord injury. When there's damage to the spinal cord, you not only lose the cells that are there, but you also lose the myelin on the axons that are traveling. And what this means is that the highway all of a sudden is no longer able to carry that information because you've lost the insulation. And so you not only lose information and neurons that have been involved in the local process, but also all those axons that are around it are going to be affected by it. So the glia cells are going to be influencing things. And so I want to go through that with you. So here's an example of what spinal cord injury looks like. Say it's a whiplash. If you have a whiplash, you're going to get damage to blood vessels. So blood vessels are going to tear inside the spinal cord. And when that happens, you're going to get swelling. There's going to be an expansion of a fluid inside the cord. And what that does, it's going to put pressure on the normal cells. So let's go through it. You're going to get a number of events. First, you have the initial damage, likely limited to a small region. So say this is the region where you got compression and damage to the blood vessels and the neurons that were here. There's hemorrhaging, so there's fluid that's released from the vessels, and of course, you know, the spinal cord doesn't have any room for anything for it to expand into, right? So if there's something inside of it that's leaking, it's going to put pressure on the normal cells. So the normal cells up here, they haven't been damaged, but because of this hemorrhaging, you're getting this pressure on the healthy neurons. Injured neurons release glutamate. What's glutamate? What is it? It's a neurotransmitter. Is it excitatory or inhibitory? It's excitatory. So when all of a sudden a whole bunch of glutamate is released, what happens is that the cells that are nearby get overexcited. And that causes damage as well. So when you have glutamate release, you get this overexcitation of the neighboring neurons. You're destroying the neighboring neurons that had not been damaged before. So you get the cyst and then you get the glutamate. The cyst also puts pressure on those glia cells. Those glia cells were providing myelin for these axons. So these axons are the mechanism by which the brain can communicate with the neurons. So you've been damaged here, but the brain is now prevented from sending information down further to the thoracic and to the sacral region, because the myelin, which was provided by those glia cells, is lost. Why? Because the glia cells get killed because the pressure on them. So you lose the myelin, and therefore you lose the ability to communicate downstream. And after a few weeks, what happens is that you get this wall of glia that forms, that basically prevents these axons from communicating. So you not only get damage to the region where you had the injury, but you also prevent communication from everything below. You prevent that information to arrive or be sent up high. So, and that's what causes paralysis. Right? So you get weakness, and then you get paralysis, and it's not just that you can't move your fingers, you also can't move your legs. So this is the mechanism of spinal cord injury. So much of the research on spinal cord injury is about containing that swelling, reducing it, and making it so that it doesn't result in this cascade of events that becomes paralysis. So the nervous system has been damaged. There's spinal cord injury. So what can one do? Well, the muscles are okay, right? So there's nothing wrong with the muscles. If there was a way to activate those muscles independent of that pathway in the spinal cord, then you'd have a process by which you can get around this damage. So how does one do that? So the process is a form of neuroengineering. So what one does is that you take a part of the nervous system that can communicate. So this person has had a damage that makes them so that they have trouble particularly flexing their fingers. So their shoulder muscles, which are sitting at a cervical level above the hand muscles, they're okay. You can reach these muscles. So a sensor is placed on the shoulder, and the accelerometer is detecting motion. When the patient lifts the shoulder, what that does, a stimulator then activates the hand muscles, allowing the patient to close the hand. So what this will allow the patient to do is to grip something by moving their shoulder upward, release it by bringing the shoulder downward. So let me show you what that looks like. Do you have any questions about that? Yeah.
Was the accelerometer implanted, or was that external?
It's implanted. Yeah, it's subdural, and the stimulator is also subdural. Any other questions? Okay. All right. So the muscles are all right. The nervous system has been damaged. What one can do is to find a way to make the remainder of the nervous system activate some external device that will allow that muscle to be activated. So what you saw here is an individual that had intact ability to control the shoulder. if they're completely paralyzed and they can't move anything, then the next level of research would be to look at activity in their brain, record activity in their brain, and then decode that to try to then use the activity in the brain to move the body part. And that's also another avenue that's being pursued. And it's, particularly important, this research these days, with all the paralysis and damage that's happened to the young men that have gone to war. So this kind of damage that you see is not just the damage of individuals that have accidents, but it's a common problem that a lot of soldiers have been suffering from. So much of this research is now driven by the desire, to basically bring back some mode of control, some mode of ability to the young people that had served the Army and the United States. Okay, so a little bit more about the anatomy. As I mentioned to you, the dorsal surface is the surface, the back, where the afferents come in, and the ventral surface is where the efferents go out. So the nerves that go to the muscles are coming from neurons that are called motor neurons that are sitting in the ventral horn, and the nerves that are coming from the temperature, from proprioception, from touch, they are coming in the dorsal surface, as you see here. So the ventral horn houses the motor neurons. So here are the motor neurons here, and they form these columns. The motor neurons consist of a cell body and an axon that then innervates the muscles. That gives you the ability to contract and to move. There's an anatomy to this circuitry such that the proximal muscles, the muscles that are holding up your body, the axial parts of your body, those motor neurons are medial, whereas the motor neurons that go to the distal musculature, the hands, the fingers, are lateral. So medial, proximal muscles, lateral, distal muscles. Ventral horn, motor neurons, distal horn, afferents. Yeah?
Does this apply to both skeletal and smooth muscle?
Well, the smooth muscles will all be medial.
Oh.
Yeah. In fact, you don't have this process, this expansion, if you look at the thoracic region. Good question. Okay, so what happens to the axon when it leaves the spinal cord? A motor axon goes out and then innervates muscle fibers. And you see it in this example here. So here's a single motor neuron. Here's this axon leaving the thoracic and then innervating a group of muscle fibers in this muscle. So a motor unit is something that consists of a single motor neuron and all the muscle fibers that it innervates. So a muscle fiber gets an input only from a single motor neuron. You only have a single parent that's controlling that muscle fiber. But a single motor neuron innervates many muscle fibers. So it's one to many. Now, the number of muscle fibers that are innervated by a single motor neuron depends on the function of that muscle. For something like your leg muscles, you have these powerful muscles, you're going to have tens of thousands of muscle fibers that belong to a single motor neuron. But for your fingers, where you need fine control, you have 10, 15, 30 muscle fibers that are controlled by a single motor neuron. For your eye muscle, you have very few muscle fibers that are controlled by a single motor neuron. So for things that you need fine control, you have motor neurons that innervate a small number of muscle fibers and a whole lot of motor neurons to control that body part, like your fingers, where you have fine control. For your legs, where you need force to be generated and you don't have fine control, like these muscles that hold up your weight, the motor unit consists of one motor neuron and many muscle fibers. Any questions? Is it clear what a motor unit is? Why is it called a motor unit? Because it's basically the single smallest unit of control for your nervous system. you can at best control a single motor neuron, but you can't control a single muscle fiber. Yeah?
This is the cause of greater variability in force.
Yes. Yes. Very good point. This is one of the causes of it. Okay. So we've learned about motor units. We can now learn something about diseases that affect motor units. One of the most devastating of those diseases is polio. So polio is a virus that attacks the neuromuscular junction and then travels up to the motor neuron cell body and kills that motor neuron. And when that happens, well, these muscle fibers become orphaned because their motor neuron is gone, which means they don't have a way to get activated. But nothing in the nervous system is ever wasted. So what happens now is that there is this process whereby the neighboring motor neurons somehow detect that those muscle fibers are no longer being activated. And what happens is that they take over. They send processes to those orphan muscle fibers, and they take over control of those. But now what happens is that you get a giant motor unit. So in polio, what you end up with is a few motor neurons that are controlling this gigantic set of muscle fibers. And so there's horrible control of those muscle fibers. Okay. Now, a muscle, which is just, the thing that makes your body capable of generating force, is actually composed of the force-producing elements called extrafusal muscle fibers. This is the thing that we think about when we generate force, but there are sensors in the muscle as well, and those sensors tell the nervous system important things about the state of the muscle. There's another kind of muscle fiber that doesn't generate force for the purpose of massive force production, and that muscle fiber is called an intrinsic muscle fiber here, and its job is really a part of the sensory system. It houses what are called muscle spindles, which is a way by which your nervous system can tell where your body is. So when your muscle is stretched, you can tell that because muscle spindles, which are wrapping themselves around these intrafusal fibers, they get stretched. And they send a signal to the nervous system saying, this muscle has been stretched. And on Monday, I'll go over an experiment with you. So basically, if you were to take your cell phone, put it in vibrate mode, and vibrate the tendon area, the belly area of your biceps, what that does is that it's activating these muscle spindles. And you'll get a sensation of lengthening of that muscle. So it's a component of the nervous system, muscle spindles, that provide length feedback information to the nervous system. The extrafusal fibers, when they're getting activated, they generate force. So these extrafusal fibers are innervated by axons. They're called alpha motor neurons. Alpha motor neurons, when they generate action potential, the action potential comes to the extrafusal muscle fiber. This is what makes a motor unit, and they generate, through generation of that action potential, a spike that becomes a twitch in that muscle. And that muscle then will produce force. So this is shown here. So here's the action potential down the nerve. The alpha motor neuron generates an action potential. The muscle twitches, relaxes, another action potential comes, it twitches. So what you notice is that an action potential has a width of about 2 milliseconds. But a twitch in a muscle can have a width of 100, 200 milliseconds, perhaps even longer. So force that's generated takes much greater amount of time than the twitch that was generated by the action potential. So if one brings these action potentials closer to each other, so instead of waiting 200 milliseconds, say you do it at a faster frequency, 20 hertz, what you're going to get, this is 50 milliseconds apart, what you see is that you get force that builds up. There's no time for the twitch to decay. And if you increase the frequency, it begins to fuse until maximally stimulated, you get this fuse. So when you maximally stimulate your muscle, this is what you're doing. And the force fuses by itself, and it doesn't allow for that decay to take place. So one way by which you can manipulate how much force you produce is by manipulating the rate of the action potentials from the motor nerve. The greater the rate, the greater the force in that muscle. But muscles are not like torque motors. So if you've ever played with a torque motor, if you give it a voltage, it'll produce some torque. And it'll do it regardless of the position of the rotor. Muscles will produce a force that depends on their length. This is shown here. So just to be clear, if you give a single pulse to a muscle, the twitch that it will produce, the force that it will produce, will depend on its length. Muscles are more like springs. The longer they are, that twitch will be bigger. This is shown in this slide. So this is the ankle of a cat that's been placed, and measurements are being made from the soleus muscle. Here's the muscle of the soleus. When this contracts, the ankle extends. It pulls down. What you're seeing here is tension on the y-axis. On the x-axis is the angle of the ankle, or the length of the muscle. So the angle of the ankle, the smaller it is, the smaller this is, the closer the ankle is to the straight up position, the longer the soleus muscle is. And if you look at the tension that's produced when you produce a single twitch, you see that the twitch is rising as the length of the muscle is increasing. If you were to stimulate that muscle maximally, what you will see is that it will produce much more force for a longer length than for a shorter length. So it's being maximally stimulated at, let's say, 100 hertz, and the force that it produces is much higher at this length than this length. Okay, so this tells you that the nervous system, in order for it to control the force that's being produced, it has to know the length of the muscle. And the length of the muscle is fed back to the nervous system from those muscle spindles. So if you've ever fallen asleep on your arm and you've woken up not being able to quite feel your arm muscle, what you've done is put pressure on this nerve here, made it so that the proprioceptive feedback has been cut off. You can't feel your arm. And what you need to do is, move the arm around, let the blood flow again, and re-allow for that transmission to take place. Without that sensory feedback, you wouldn't know where the arm is located, and you would have a heck of a time trying to control the force in that muscle. So one of the problems that besets individuals with neuropathy, sensory neuropathy, is damage that kills those sensory afferents, those afferents that bring sensory information to the spinal cord. And that basically is like having numbness in the body part all the time, making it incredibly difficult to generate accurate movements. Okay, any questions so far? All right. So next what we're going to do is try to understand the relationship between forces that muscles produce and the torques that they produce. And in high school, you learned a little bit about moment arms, the relationship between force and torque through the moment arm. I want to teach you a little bit more about this so we learn something about biomechanics and understand where do moment arms come from. The idea is that when something produces force, let's say a muscle, it is doing work. Force times distance is work. And the work that you measure should be the same regardless of the coordinate system that you measure it. Force times distance, work, energy, should be the same as torque times displacement. So you have some angle that you're trying to relate to torque. So say my elbow angle. I'm going to generate some torque here, and it's going to cause a motion. So the idea is that the torque and the displacement in joint that I had is the same as the force and the displacement in length that it had. The work is the same in those two coordinate systems. And by relating the work in one coordinate system to another, we can understand the relationship between force and torque. And that's what these equations are going to show you. So let me go over it one more time. When you generate torque on the elbow, what you're doing is that you're generating something that's going to cause a displacement by some amount, angle. Torque times angular displacement is work in angular coordinates. But that should be the same as force in the muscle times its length change as you did that. And when you relate those two things, you get work is equal in these two coordinate systems. And then we can relate how muscle length changes produce force and the relationship between forces and torques. Now, why is it important to do this? Because you can think about a moment arm when it's just a single joint and a muscle. But what if that muscle wraps itself around something and also goes and acts on a part of the body downstream on a second joint? What is a moment arm then? It's not so easy in that case. But the same principle that I'll show you will allow us to understand how to get torques from forces, despite the fact that having very complicated geometries. So we're going to first relate work in one coordinate system, tau times delta theta, that's the joint coordinates of work, to force in the muscle coordinate system, lambda. So here we have a model of triceps. Triceps has some length. And here's the elbow. It has some force that it's going to produce. It's going to cause a change in the length of the muscle. It's going to produce a torque on this joint, which is going to cause a change in the angle of the elbow. So tau d theta is force d lambda, where they're negative because this force is causing a length that's decreasing, but it's doing work. Whereas the torque, this is what we call an angle that's increasing in this way, and the torque that's increasing. So force times negative of delta lambda would be a positive number, is equal to torque times delta theta. Muscle contracts to generate a force. Okay, so we have this relationship between a change in the joint angle and a change in length. So we can write this as follows, and then replace this with a derivative, d lambda d theta, which says that force times the derivative of length change in muscle coordinates with respect to joint coordinates is torque. So we need to write what is the length of this muscle in terms of the angle theta. And that's shown here. This is the law of cosines. So this tells you, if you know theta, what is lambda. Next, what we need to know is the relationship between the change in lambda with respect to a change in theta. So the derivative of this function with respect to theta. So what we have is that we have a quadratic, we have a square root, we take the derivative of that, and so we get this function is to the 1/2, so the derivative of that with respect to theta is to minus 1/2, so it goes in the denominator. Then we have this term in the square root itself, which the derivative of a cosine is a sine. So this is our derivative. Now why is this useful? Because this is what we're going to use to relate force with torque. All right. Now, in high school, you learned that, well, there's this thing called a moment arm. Now, here's the moment arm, right? So this is the muscle that we're talking about. It's going to act on this joint, and you learn that, well, if I take this muscle and I find a perpendicular for it to this joint, C, then by multiplying the force by this, I will get torque. Let me show you why that's the same thing as this principle of work that I showed you. So C, this length here, is B times sine of alpha. Here's alpha, here's B, and this is C. So that's just geometry, that's just a trigonometric function relating the sine of alpha to the height and the hypotenuse. Okay, then the law of sines says sine of alpha over A is sine of theta over lambda. So sine of alpha over A is the same as sine of theta over lambda. Okay, so if that's the case, I can rewrite C, B sine theta, as AB sine theta divided by lambda. And so here we have it. Here's lambda, my equation that I had in the previous slide, in the denominator. Here's AB sine theta. So look, d lambda d theta is C. That's what we call the moment arm. Okay, now why is this important? Why is this useful for us? Because when we define it using work and the concept of equal work in these two coordinate system, then I can have a very complicated lambda. I can have this guy going around some joint, pushing on some other place, and I can ask, well, how does this length change with respect to this theta? Or some other theta. I could have multiple thetas now. And so I can find the derivative with respect to not just this joint, but also this joint. So I can have two thetas that the muscle can wrap around. And when that happens, I can use this idea, d lambda d theta, to find the torque that it produces here as well as the torque that it produces there. Okay, so now we have two muscles. We have a muscle that is going to be a flexor. We have a muscle that is an extensor. This muscle, when it produces force, it pulls up. This muscle, when it produces force, it pulls up over there. So this causes flexion, this causes extension. So force produced by this muscle produces a torque we're going to call tau 1. Force produced by this muscle is going to produce a force we're going to call tau 2. And their relationship is based on the derivative of their length change with respect to theta. The total torque that's acting on the muscle is the sum of those torques. And so you have a flexor, you have an extensor. The torque that you feel on this joint is the sum of the force produced by each of these times their this d lambda d theta. This d lambda d theta is called the Jacobian. Jacobian is a transformation from one coordinate system to another using this differential representation, d lambda d theta. So force times d lambda d theta gives you torque. Force in each muscle gives you torque, tau 1, tau 2. The sum of that is the total torque. So, for example, if I activate my biceps with a lot of force, it's going to produce a torque upward. If I activate my triceps with a lot of force, it's going to produce a lot of force downward. The sum of those two will cancel, give me 0 torque. That's when my arm doesn't move, but I'm producing tons of torque. They just happen to cancel. And what I'm doing is stiffening my arm without moving it. Any questions so far? All right. So we're now moving toward describing voluntary movements. So we have muscles that produce force. And you have two muscles, so when you activate one and you activate the other, depending on the torques that they produce, your arm will settle to some position where these two torques cancel each other out precisely. So what this means is that you have some activity on the biceps, you have some activity on the tricep. They're like two springs. You're tightening this one, you're loosening that one, and what that means is that the arm is going to settle to some position regardless of where it starts from. And that's the equilibrium position of your system. The two springs give you an equilibrium position here. If one muscle doesn't produce a lot of force, the other one producing more force, and if I increase this force, it's going to give me an equilibrium here. Okay, but is that how I move? By just changing the level of force in the muscle so that the arm moves to new equilibrium? No. If that's how you were to move your body, you would move rather slowly. Here's how it would look like. So suppose you increase the activity in muscle 2. So here's muscle 2. Suppose you were to increase its activity from some baseline level. What that means is that the arm will slowly move to some new position, and it will stay there. But look at the time scale, 4 or 5 seconds. That's an incredibly slow movement. You don't move so slowly. So how is it that you can make rapid movements? It's because this is how you do it. You excite the agonist, this guy here, by a large amount while you shut off the antagonist, this one here. Then you brake using activation of the antagonist. And finally, you nudge it a little bit using the agonist. So in order to move rapidly, you put on the accelerator, activate this while shutting off this agonist. Then you put on the brakes using the antagonist. And then finally, you nudge it in place with the agonist. It's a 3-burst of activity. Agonist, antagonist, back to agonist. This is what it looks like in real. So here's the wrist of an individual making a rapid movement. And if you look at the muscles as they're making this movement, what you see is that here's the movement. Look at the time scale here. 100 milliseconds. So pretty rapid movement. This is the velocity, about 300 degrees per second. As the movement takes place, you get the agonist that shows a burst. It accelerates. Then you have the antagonist that puts on the brakes. And finally, the agonist that nudges it back into place. So it's as if fast movements are like being at the red light and putting on your foot on the accelerator and then putting on the foot on the brakes until you stop at the next position. Agonist, antagonist, agonist. As you see by these EMG measurements. That's what a fast movement looks like. Okay. So the final thing I want to show you. Remember that we talked about the cerebellum. We talked about the ability to use the cerebellum to make fine movements, to time your actions so that they're precisely made at the right location. And without a healthy cerebellum, what happens is you get problems in movements. So now that we know how a fast movement is made, let's look at the cerebellar patient. Let's look at an individual who's had damage to their cerebellum and look to see how they make a movement. What we're going to see is a problem associated with being unable to activate those EMG patterns at precisely the right time because they're relying on feedback rather than prediction. And as a result, the hand goes into a tremor. So let's see what that looks like. So here's a healthy individual making that wrist movement, that fast movement that I was showing you, 200 milliseconds. Look what happens. So here's the wrist flexing, the position of the wrist. Here's the flexor, burst, extensor, break it, and then finally the flexor. So the arm is perfectly stable. And you would think this is a simple thing, right? Anybody can do that. But let's see what the patient with cerebellar damage can do when you're asked to make the same movement. So here's their movement. They make that fast movement just fine, but look, they can't hold it. They have oscillation at the end of it. It moves, but it can't hold. This is tremor that's resulting at the end of the movement. Why? Well, let's look at the EMG. Let's look at the timing of that EMG. Let's look at the bursts and when they're occurring. What you're seeing is that you get this agonist that makes the movement start. The antagonist is coming, and then that agonist burst is coming too late. Look what is happening. This is already, the velocity has already reached a peak that's positive, whereas here it's still negative, has an opportunity to basically come earlier. And so this timing comes because you have this exquisitely fine control in your cerebellum that allows you to send these commands at the right time and the right place. So a patient with cerebellar essential tremor, they can move. They just can't move well. So that agonist burst is fine. Everything that comes afterwards is too late. Any questions? All right, so as you can see, it's really a miracle that, we spend years, I'll come to you in a second. We get old, and if you're lucky and if you get old healthy, you've been able to have a lifetime of good movements. And it's astonishing how things have to be precisely on time to make a simple movement like a wrist flexion. Okay, yes, sir.
So you compared a normal wrist movement to like
holding down both the gas and the brake on a car, isn't that inefficient? Is there like any strain from like the two muscles fighting against each other?
Well, so look at what happens. So let's go back to this. When the agonist is activated, the antagonist is shut off. So you see this reciprocal activity until the end where there is some co-activation of both. Not so well seen here. Let's go back to this where we can see it a little bit better. So there's some amount of activity. When this becomes active, this is shut off. Then when this antagonist becomes active, the agonist is shut off. And then finally, this here, you have activity in both muscles. So to hold still, you need to have activity both agonist and antagonist. Will determine then the position. So holding still is an active process. You need co-activation. But during the movement, you shut off the one that's, antagonist to the action you're trying to do. Was there another question? Okay. Thank you so much.